Let's take a quick look at aromatic compounds today. After the theoretical part, you will be tested in workshop 1. To do this, go to your office. The invitation letter was sent to you earlier. If you do not see the letter, go to the spam folder and look there. If you still haven't found the letter, email me about it at webmasterjam@gmail.com. I will send you login details. Species and herbs have long played a romantic role in the course of history. They bring to mind frankincense and myrrh. And the great explorers of past centuries, Vasco da Gama, Christopher Columbus, Francis Drake, and Ferdinand Magellan, whose quest for species helped open up the Western worlds. Truth not without risk, trade in species was immensely profitable. It was natural therefore that species and herbs were among the first natural products studied by organic chemists. If one could extract from plants the pure compounds with the desirable fragrance in flowers and determine their structures, perhaps one could synthesize them in large quantity at low cost and without dangers. Okay, next slide. Some facts about benzene. It turned out that many of these aromatic substances have rather simple structures. Many contain a six-carbon unit that passes unsketched through various chemical reactions that after only the rest of the structure. This group C6H5 is common to many substances, including benzaldehyde, mm, isolated from the oil of BTA almonds. Benzoyl alcohol, benzoyl alcohol, isolated from gum benzoin, a balsam resin obtained from certain sulfastasian trees, and toluene. Toluene, a hydrocarbon isolated from tolu balsam. When any of these three compounds is oxidized, the C6H5 group remains intact. The product is benzoic acid, another constituent of gum benzoin, the calcium salt of this acid. When heated, yield the parent hydrocarbon C6 H6 benzene. Next. Despite its molecular formula, benzene for the most part does not behave if it were unsaturated. For instance, it does not colorize bromine solution the way alkenes and alkynes. Not is it easily oxidized by potassium permanganate. It does not undergo the typical addition reaction of alkenes or alkynes. Instead, benzene reacts mainly by substitution. For example, when treated with bromine Br2 in the presence of ferric bromine as catalyst, benzene gives brombenzene and hydrogen bromide product, for example. Chlorine with a ferric chloride catalyst reacts similarly. Uh, Only one monobromobenzene or monochlorobenzene has ever been isolated. That is, no isomers are obtained in either of these reactions. This result requires all 6 hydrogens in benzene to be chemically equivalent. It does not matter which hydrogen is replaced by bromine. We get the same monobromobenzene. This fact has to be accounted for in any structure proposed for benzene. When brombenzene is treated with a second equivalent of bromine and some type of catalyst, 3 dibromobenzenes are obtained. The isomers are not formed in equal amounts. Two of them predominate and only a small amount of turned S isomer is formed. The important point is that there are 3 isomers, no more and no less. Similar results are obtained when chlorobenzene and fused chlorinated to give dichlorobenzenes. This fact also have to be explained by any structure proposed for benzene. The problem of benzene structure does not sound overwhelming, yet it took decades to solve. Let us examine the main ideas that led to our modern view of its structure. Okay, orbital model for benzene. The calculus structure of benzene. To explain benzene negative tests for unsaturation, that is, it failed to decolorize bromine or to give a permanganate tests. Calculus suggests that the single and double bond exchange positions around the ring so rapidly that the typical reaction of alkenes cannot take place. Orbital theory, which is so useful in rationalizing the geometries of alkanes, alkenes, and alkynes, is also useful in explaining the structure of benzene. Each carbon atom in the benzene is connected to only mm, uh, 3 other atoms. 2 carbon atoms are a hydrogen. Each carbon is therefore sp2 hybridized is in ethylene. 2 sp orbitals of each carbon atom overlap with similar orbitals of adjacent carbon atoms to form the sigma bonds of the hexagonal rings. Hexagonal rings, please. The third sp2 orbital of each carbon overlaps with a hydrogen 1s orbital to form the CH sigma bonds. CH sigma bonds. Perpendicular to the plane of the 3sp orbital at each carbon is a p orbital containing 1 electron, the 4 valence electron. The p orbital on all 6 carbon atoms can overlap laterally to form p orbital. Laterally overlap uh, create laterally to form p orbitals that create a ring or cloud of electrons above and below the plane of the ring. The construction of a benzene ring from 6sp2 hybridized carbons is shown schematically in figure. This model explains nicely the planarity of benzene. It also explains its hexagonal shape with HCC bond and CC3 bond angle of 120 degrees. Next slide. Nomenclature of aromatic compounds. Because aromatic chemistry developed in a haphazard fusion many years before systematic methods of nomenclature were developed, common names have acquired history, respectability, and accepted by UPAC. Examples include, benzene, toluene, cumin, styrene, phenol, methoxybenzene, benzaldehyde, acetophenone, benzoic acid, aniline. Next, monosubstituted benzenes that do not have common names accepted by UPAC or named as derivatives of benzene. For example, bromobenzene, chlorobenzene, nitrobenzene, nitro group, position, ethyl radicals, ethylbenzene, propylbenzene. Specific examples are when two substituents are present, three isomeric structures are possible. They are designated by the prefix ortho, meta, and para, which are usually abbreviated as ortho, meta, and para, respectively. If substituent X is attached by convention to carbon 1, then ortho group or 1 carbon 2, 6 position. Meta group 3, 5 position. Para group position 4. The prefixes ortho, meta, and para are used even when the two substituents are not identical. Ortho dichlorobenzene, meta dichlorobenzene, para dichlorobenzene position 1, 4, paraxylene, for example, and para-chlorobenzene sulfanoic acid, sulfur group SO3H. Although M and para designation are commonly used in naming the substituted benzenes, positions, number of substituents can also be used. For example, ortho-dichlorobenzene can also be named 1,2-dichlorobenzene, and metachlorophenol can also be named 3-chlorophenol. When more than two substituents are present, their position are designated by numbering the ring. For example, 1, 2, 3 methyl benzene, 3, 5 dichlorotoluene, and 2, 4, 6, 2, 4, 6, 3 nitrotoluene, TNT. Aromatic hydrocarbon as class are called arenes. The symbol arene is used for an aryl group, just as the symbol R is used for an alkyl group. Therefore, the formula aryl R would represent any aryl alkane. Two groups with special names occur frequently in aromatic compounds. They are the phenyl group and the benzyl group. Phenyl group, for example, C6H5, and the benzyl group, C6H5 and methylene group. The symbol phenyl is sometimes used as abbreviation for the phenyl group. The use of these group names is illustrated in the following examples. Example: uh, 2-phenylpentane or 2-pentylbenzene, position 2. Phenylcyclopropane, cyclopropane, radicals phenyl or cyclopropylbenzene. Next, 1,3,5,3-phenylbenzene, 3-phenylbenzene, position 1, 3, 5. Biphenyl, and benzyl chloride, radicals C6H5 benzyl, radicals benzyl chloride, metanitrobenzyl, alcohol, type compound, alcohol, functional group OH, positional nitro group metanitrobenzyl alcohol. Next slide. Electrophilic aromatic substitution. The most common reaction of aromatic compounds involve substitution of other atoms or group for a ring hydrogen on the aromatic unit. Here are some typical substitution reactions of benzene. For example, benzene reacts with chlorine, bromine, and acid nitration. In presence catalyst reaction in presence of ferrum Cl3, acid Lewis product monochlorobenzene and hydrochloric reaction chlorination. Next analog reaction, benzene plus Br2 in presence ferrum bromo 3 product monochlorobenzene HBr reaction bromination, and reaction benzene plus acid nitrate in presence sulfuric acid concentrated form nitrobenzene, and water reaction nitration. Most of these reactions are carried out at temperatures between about 0 Celsius degree and 15 Celsius degree, but these conditions may have to be milder or more severe if other substituents are already present on the benzene ring. Also, the conditions can usually be adjusted to introduce more tan on substituent if desired. Next slide. Ortho para direction and meta direction groups. Substituents already present on an aromatic ring determine the position taken by a new substituent. For example, nitration of toluene gives mainly a mixture of ortho and para-toluene. For example, toluene reacts with nitrate acid, product, two product, ortho isomer, and para-isomer. Ortho isomer 59%, para-isomer 37%. Meta-isomer low 4%. On the other hand, nitration of nitrobenzene under similar conditions give mainly the meta-isomer. For example, Uh, this pattern is also followed for other electrophilic aromatic substitution, chlorination, bromination, sulfonation, and so on. Toluene undergoes mainly ortho-para substitution, whereas group are ortho-para directing and others meta-directing. Next, list some of the common groups in each categories. Let us use see how the electrophilic substitution mechanism account for the behavior of the two classes of substituents. Consider denaturation of toluene. In the first step, the neutronium ion may attack a ring carbon that is ortho, meta, or para to the methyl group, for example. In none of the three resonance contributors to the benzonium ion intermediate for ortho or para substitution, show in blue dash boxes. Blue dash boxes. The positive charge is on the methyl burning carbon. That contributor is chiefly carbocation and more stable than the other contributors, which are secondary carbocations. Station. However, with meta-attack, all of the resonance contributors are secondary carbocation. The positive charge in intermediate benzonium ion is never transferred to the methyl substituent. Therefore, the methyl group is ortho-para directing so that the reaction can proceed via the most stable carbocation intermediate. Similarly, all other alkyl group for ortho-para direction. Ortho and para direction. Next slide. Directing and activating effects of common functional groups. Groups are listed in decreasing order of activation. For example, amino group, big activation, directing and ortho-para direction. Next, hydroxyalkoxy group, alkylamino, alkyl, galogen group. Next, direct acyl carboxy group, deactivating group, meta direction, for example. Carboxido, carboalkoxy, carboxido, carboxamido, and carboalkoxy, sulfonic acid, cyano acid, and nitro group. Polycyclic aromatic hydrocarbons. The concept of aromaticity, the unusual stability of certain fully conjuncate cyclic system can be extended well beyond benzene itself or simple substituted benzenes. Coke required in high quantities for the manufacture of steel is obtained by heating coal in the absence of air. A byproduct of this conversion of coal to coke is a distillate called coal tar, a complex mixture containing many aromatic hydrocarbons, including benzene, toluene, and xylene. Naphthalene, for example, C10, H8, C10H8, was the first pure compound to be obtained for the high boiling fractions of coal tar. Naphthalene we easily isolated because it sublimes from the tar as beautiful polarized crystalline solid. Multiple point multi-point 80 degrees Celsius. Naphthalene is a planar molecule with two fused benzene rings. The two rings share two carbon atoms. The bond lengths in naphthalene are not all identical, but they all approximate the bond lengths in benzene, 1.39 angstrom. Although it has two six-membered rings, naphthalene has a resonance energy somewhat less than twice than of benzene, about 60 kilocalorie more. Because of its symmetry, naphthalene has three sets of equivalence carbon atoms. Like benzene, naphthalene undergoes electrophilic substitution reaction, halogen, nitration, and so on. Usually under somewhat mild conditions, that benzene. Always two mono-substitution products or possible substitution mm, at C1 usually predominates. Next slide. Naphthalene is a parent compound of a series of fused polycyclic hydrocarbons. A few other examples of which are anthracene, phenanthrene, and purine. Thank you for attention. Start testing. Practicum 1. See assignment in Google Class.